up, so let's keep going here. So let's look at a flow chart here that kind of just walks us through all of the events that are taking place. And again, just setting some context here, all of this is happening super fast, right? I can't even appreciate what 1 millisecond looks like. And so this is happening extremely rapidly. And the reason why is because it needs to. When I think about moving my upper limb or moving my fingers or talking or walking, I don't need there to be any delay time between the instructions sent from my brain and the actual movement of muscle. So these events are happening extremely fast, lightning speed, as far as the communication and these signals being sent to the brain, from the brain to muscle, and so on. So let's start here by looking at the first condition is that we get a threshold stimulus, which is a stimulus that gets to -55. We now see the depolarization of the membrane. And remember, depolarization is another way of saying the inside of the cell, instead of being negative, now becomes positive because we have the movement of sodium into the cell. And remember, sodium is moving into the cell because that is its ECDF, okay? So kind of bear the things that we've been talking about as we've been building up this conversation in your mind. So we open up sodium channels, membrane permeability for sodium increases, and so we see sodium rush into the cell, which is responsible for that upstroke or the depolarizing part of the action potential. Now we describe this as being a positive feedback event. Positive charge is entering the cell. It's taking us away from set point. And so this is a brief period of time where we want to be moving away from that -70. We've got a 1 millisecond delay event that is signaling the inactivation gates to close on the sodium channels right after the depolarization begins. So when we get to that -55, there's a voltage sensitive nature of this channel, of this gate specifically on the channel, and a timed sensitive nature of this gate on the channel. And so there's a 1 millisecond delay that will inactivate this channel after that time. So then sodium channels close, essentially the inactivation gates close, and then the membrane permeability for sodium decreases. I don't know whether there's an arrow here, but you can put an arrow in on your own notes. There should be a down arrow here. So the membrane permeability for sodium decreases, and that decreases the amount of sodium that's flowing into the cell. Now, again, the coordination of these events is such that that 1 millisecond also coincides with the opening up of potassium channels. So the timed nature here for both of these channels, the inactivation gates on the sodium channels and the potassium channels themselves, is coordinated perfectly so that these things can happen at the same time. We open up those potassium channels, and so we're doing this at the same time that sodium channels are closing, and so we now increase the membrane permeability for potassium, and potassium can start flowing out of the cell, which essentially is allowing more positive charge to leave the cell, and so we start repolarizing that membrane potential. There should also be an up arrow here, so we increase the membrane potassium permeability, and we decrease the membrane sodium permeability. So just make sure you put those arrows in on your notes. And so this can be thought of as a negative feedback event because we're getting back to our resting potential, back to that -70. And so a change that's going to help us get back there can be thought of as a negative feedback event. All right, so here's a really nice summary table that kind of highlights some of the important differences between the cell at rest, the depolarizing events, the repolarizing event, and then what's happening after hyperpolarization. So a really good study tool to make sure that you've got some of these concepts going. You can even add in another row here that talks about whether it's a positive feedback or negative feedback. And you can kind of make this table your own as a good study tool. Same here. So this one compares graded potentials to action potentials. and how they differ. So for example, we can see summation of graded potentials, but we cannot see summation of action potentials. Remember, an action potential will always have the same quality, the same duration, etc. Graded potentials are different. They can be graded. They can vary in their quality. They can be small. They can be large. They can have different amplitudes, different duration. Also, the channels that are involved. So for example, graded potentials are going to be happening at the soma. So these are going to be the ligand-gated channels, the soma and the dendrites, whereas action potentials are going to be along the axon, and these are going to be brought about by those voltage-gated channels that we've been speaking about. You can also think about the ions that are moving, right, that are helping with the graded potentials versus action potentials, etc. Okay, what questions do we have at this point? Any questions? So I'm gonna have you guys break off into some groups here, some breakout rooms, and discuss these 4 questions, and then we'll reconvene in a couple minutes. So let's see here. First off, okay. All right, any other questions, guys? Any other questions that have come up about this, about what we've talked about so far? We're going to now move into speaking about the refractory periods. And the refractory periods are important in understanding why the action potential is all or nothing, and why they are always identical, and why they're always traveling in one directional, why they're unidirectional, okay? So there are 2 refractory periods. Okay, I see one question here, so let me address this. So someone's also asking about whether or not we could disrupt the action potential, so whether or not we can slow it down or speed it up. And the answer is we cannot slow down or speed up an action potential itself. We cannot change the quality of one action potential. What we can do is increase the frequency, how fast they're being fired or how slow they're being fired. So for example, this is how we appreciate different stimuli. So the difference between a really loud sound or a high-pitched sound and a low-pitched sound or a quiet sound are the difference in the frequency of action potentials. Another example that we'll look at in muscle when we get to skeletal muscle is if I'm lifting a very light object like a piece of paper, I'm going to be calling on maybe 1 or 2 neurons that are innervating that muscle. They're going to be firing action potentials at maybe a medium to intermediate rate. But if I am lifting something extremely heavy, I am going to be calling on more neurons, and they're going to be firing action potentials much more rapidly in order to appreciate the difference in that stimuli. So that's the way action potentials can communicate different types of stimuli and can, have variation in terms of the outcome that's brought about, but an action potential in itself does not change. Okay, the way that we put them together can communicate different types of signals. Okay, that was a really good question, so thank you for those questions. All right, so we said that there are 2 refractory periods. And so kind of just going into the point that I was just making, action potentials can only increase their frequency to a certain point, right? Because we cannot fire an action potential while an action potential is going on. We also cannot fire another action potential immediately after one action potential has been completed. Okay, and so there's a period there where the cell cannot be excited again, no matter how strong the subsequent stimuli is. And so there are 2 periods here. There's the absolute refractory period, and we talked about what contributes to this. This is the inactivation of sodium channels because of the closure of those voltage-gated sodium channels, specifically the inactivation gate on those channels. And because they remain closed until the membrane potential gets back to rest, we physically could not fire another action potential no matter how hard we tried. Okay, it's physically not possible. The duration of the absolute refractory period is pretty much the entire length of an action potential, which kind of makes sense, right? An action potential must come to an end for another action potential to begin. So the absolute refractory period is the period while an action potential is happening, we're not back down to rest. And so even if we have the strongest of stimuli, we could not fire another action potential just yet. Now, the relative refractory period is a little bit more laxed. This is because of the opening of potassium channels. So we still have potassium channels open. And so the membrane potential is still looking quite negative as potassium is still actively leaving the cell. And so here it's going to be harder to fire another action potential, but it's possible, okay? If we have a very strong stimuli that can kind of overcome or counteract the negative environment that we're experiencing here at about -85 or so, it's going to take a stronger stimuli, but we can fire an action potential, okay? So in other words, it's harder to depolarize a cell from -85 to +30 than it is to depolarize the cell from -70 to +30, but it's possible. It's just going to take a stronger stimuli. And so the relative refractory period is slightly longer. It's about a couple milliseconds after the actual ending of the action potential. And that relative refractory period is pretty much the duration of hyperpolarization. And so the cell is in its relative refractory period until we get right back to -70, where it's opening up of those inactivation gates on sodium, and all of the potassium channels have closed by this point. And so we start back from our resting state again. And so this is what keeps each action potential as a separate all or nothing event. We can't combine them because we cannot fire another one during one, and we cannot easily fire another one immediately after one has ended. And so the absolute refractory period prevents another action potential from being generated right away. It's because of the closure of the inactivation gates on sodium. And it's also what helps to keep the action potential going in one direction. So remember I talked about this kind of infectious nature of the action potential moving or propagating down the length of the axon. If I depolarize one segment of the axon and the adjacent segment becomes depolarized, the previous segment is now in its refractory period. And so the infectious nature of the action potential cannot be spread backwards because the previous segment of the axon is now in its refractory period, okay? And so that's kind of the importance of the absolute refractory period. The relative refractory period is pretty much the last part of repolarization and the extent of hyperpolarization. This is where it's harder to fire an action potential. And this is because sodium gates are closed and are inactivated. The inactivation gates are closed. So when we say that the gates are inactivated, this means that they're closed and incapable of opening, because although the activation gates may still be open, the inactivation gates are closed. Okay, and because that's kind of still wrapping up at this point, right? Remember, we had the closure initiated at +30, but it doesn't all happen at once. And so as we're still closing up some of these sodium gates, it's possible to fire another action potential, but harder.